All right, so what are my claims? My claims are that these are the two particles that Fermilab found. This is right from Fermilab's thing on this 10 years ago, even more than that. Don Lincoln put this up and he said, this is a fixed particle, never changes size, has a glowy edge around it. This is a point particle, it has no size whatsoever, and it can get big and small, but it has no mass. This has all the mass. I agree with that totally. And we found them using light, a pulsed red laser, and green and blue, and we could see the actual particles. And they are the particles that are described as the smallest particles that they could have ever seen. Now, you put two of them back to back like two-bar magnets, and you have a photon. One set, just the two together, they call it a gluon now, is what I call is really a dipole electron. That's my theory since forever. Dipole electrons. So they don't just have a negative side, which is glowy. They have a black side. The black side does all the movement. It pushes the white side. And here it is right here. This is, again, from Fermilab. This is not me. Fermilab put that up, and they said these are the particles. And these are the other thing that Don Lincoln put up was the Dirac neutrinos. Now we're talking about neutrinos. Now he's calling that matter and antimatter. That's backwards. This is the matter, has all the weight, that has no weight and has all the energy. And that's, but they are a black and white particle. I don't disagree with that. Or energetic and white and black. The black never changes. It's the same size, the blue, the green, the red, doesn't matter. And they, back to back, they're good to go. The black will congeal into a big round ball. It doesn't mind being next to each other. The white ones, no. They want, that's why you get this kind of separation pattern. This is not the kind of pattern they think where the flap goes this way and that way and so forth. This is a single slit. It's coming out of here. When the white comes out the other side, it sets up these, they call them interference patterns. And they're not interference like interference this way. They're get out of my way, get out of my way, get out of my way. And they create these showers in this way. Now, this light is being accelerated. It's being accelerated. And I'm going to show you what it is before it's accelerated. The particle that was inside of the light, inside of the field, that tiny little particle is now rocket shipping out of there through the Venturi, which is a natural accelerator. There's no... Now, what were we looking for? Muons and electron showers. Well, guess what? Again, not my picture, muon neutrinos, creating sterile muons because of Cherenkov radiation, which is used in the nuclear reactors to slow down the particles. Electron neutrino creating electron showers. The black one and the white one, here they are right here. The black stays back and the white goes through, and it reattaches with black over here. And as far as I'm concerned, there must be more black than there is white laying around, or I don't know if they're the same amount, but I don't think these black ones jumped ahead to recombine out here. The white ones were separated. So now you got black here, you got white here, and now you got black coming back to the white. When those black come back to the white, they create Higgs fields. They had it totally backwards. They think the Higgs fields separate. I mean, when they separate, they create the fields. No. When they come back together, that's when they create the fields. See that? That's just the light, just as it's starting to accelerate. Before, you would have never even known it was here. It would never even be seen. Now it's starting to accelerate, and the particle is here saying, everybody get out of the way, get out of the way, get out of the way. And they're all glowing as this thing comes through, which is a big ball of field. It's a field around that tiny particle. You want to see what the fields look like in space? You see this. All right, this is the solar system right here. These are all the fields that surround the solar system. They're everywhere. Light slows down coming through this. This is just crazy, this Webb telescope. Oh, there are billions of miles to go. No. It's just slowing down as it comes to us, bop, 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 through these fields. These things could be very, very close. Because and there is no homogeneousness to it, so there's no way to tell how fast it's slowing down. The more density in front of it, the more fields. The less fields, it's just going to keep going. So, they're right. If it was a total vacuum out there, it'd be a whole different story. There's not. Just push to shove, push, shove, push, shove, push, shove. And that slows down the particles. There's absolutely no way that Webb telescope is going to give us information about the size of the universe or how far things are. It's just not going to happen. All right, so you saw the particles from Fermilab and CERN, and you saw, but they use huge things. When they smash them, they're smashing things like this together. Two globs like this come and hit, and they get smashed, big, huge things, and they just sort through it, and they found the smallest ones are here. We started with the smallest ones to begin with, and then we split those apart. That's fission and fusion. There is no other way to look at it. The black came away from the white and created sterile muons, and that is dark matter, and that is also gravity. The white wants nothing more than to be attached back to that black, as you can see them reattaching here. And it's still the same size particle here as it is over here. And the only reason we can see it is because it's sitting on top of the white, so the white can't get to us. Otherwise, you won't see that. Dark matter, you can't see it. It doesn't reflect, it doesn't emit, and it doesn't absorb. It doesn't do anything. It's a pusher. However, if the white is trying to get at us and it's in the way, the white doesn't hit us. And the only way you can do that is to separate them on this level, which we did. Because once you get to the atomic stage, where they completely surround the core, which is the dark matter, you're never going to see that black particle. The only way you can do it is to separate it just like we did. And the same thing they do with the atomic smashers. They see them come apart, but they see it and they say, that's interesting. They have no idea where it came from. They say it's a particle zoo. There's hadrons. There's axions. They come up with something every day. There's new name virtually every day. Quarks and gluons and... It's a particle zoo. But everything there is starts with these two particles. And these two can be separated, which is fission. When you break them in two, that's fission. And when you put them back together, it's fusion. There is no other way to look at it. There's no other way. Fission, raw energy, and fusion. What if we could make that raw energy in that shower? What would it do to the actual energy chart? Elon Musk, please pay attention. Please, my friend, this is important. You're the guy that wants to save us money. We can save a lot of money, and you could probably sell a lot of cars. All right, so Elon, don't forget, you cannot see everything in space with the Webb telescope and see the distances. It makes no sense. The other thing is Bill Nelson heading up the NASA. He wants to spend another $6 or $8 or $11 billion to go pick up the samples on Mars. The samples on Mars we already have here. They got the same thing. Bennu, they went out and collected up, spent billions there, and they can't accept the fact that it's heart muscle. And it's not deniable. The only way you can deny it, here's what they came back with. Where is it? Right here. Oh, hold on a second. Let me go find it. Hold on. That's the heart muscle right there. And that's what they came back with. It's another tremendous waste of money. This is a heart. They went out here, and this is Bennu. They went deep inside and picked up a chunk of stuff, and it ended up being actual muscle. This is heart muscle. Those are sarcomeres. Get a biologist, get an anatomist, get somebody who's got some common sense. These are the phosphate surprise. They're phospholipid membranes. This one, then the sarcomeres, then another one, then more sarcomeres, and they just go deeper and deeper and deeper. And this is what they brought back, and they can't, and it's got amino acids, the same things that are in DNA and RNA, exact same stuff. It's got moisture. It's got all the same minerals and metals of a heart, and it is a heart. Do you see this? You see the heart valves? This is what a heart is. This is psyche. Gigantic, it's out in space, and the same thing. It's another gigantic heart in space. Oh, I can't believe that. Well, what's this tube sticking out of here? That is a heart in space. And then they say, we know it's all metals. Well, what are metals? Metals are what's in the blood. And then they show it as being melted. This is not real. This is they changed this and showed it as if it was turned into metal, which it will. And they break right off here, right there, and you end up with this, which is what Bennu is, right here. Well, that's Psyche. Bennu, as I just showed you, the same thing, right here. There it is right there. You see the heart valves? There's a big one right down here. You see that big round thing right there? And then you got the two other ones up here. This is a heart. And when they came back with the sarcomeres, it blew their minds. And they won't let me speak. I got blocked when I said, this, you have a heart. I was on the live thing the other day, and I was a little aggressive, but they blocked me. Which I always get blocked everywhere. When I showed all this stuff we had here to Don Lincoln at Fermilab, he blocked me. And called me names and was kind of very, very arrogant, nasty, obnoxious. And I'm showing the same particles he had. Now, this is over 10 years ago. And at the same time, the Russians were doing experiments in space, and we could see these black and white particles. Where's the Russian one? Here it is right here. You see this? This goes back to 2015, I think, maybe even 2014. And I contacted the Russians, and I contacted Don Lincoln at the same time. And once again, obnoxious and abusive about this. And I said, can we talk about this black hole? And this is in their experiment. They freaked out when they saw this. This is right here. During the experiment, we contacted the Earth guys who couldn't believe it either. Now, I was really close in on all of this stuff. I was on everything. Nobody paid attention to me because I wasn't, sitting there looking for funding like they were. I was looking for answers, and I got them, and they won't accept them. This dark matter is the same dark matter I just showed you that was in the center, or we could separate. They're the muons. In space, they can go or get surrounded by the white. This was my dipole electron flood theory. All right, and now in cryogenic cold, which is the coldness of space way out in the mist, where there's tons of particles, but it's not hot. In that area, guess what it does? It turns into DNA. I'm not kidding you. Well, I don't know if it's DNA, but it damn sure looks like it. That's it right there. That was done. You see these? This is just exactly the double helix and all these. And these are the amino acids. These are amino acids. They say space smells like steak. We got to come around to reality. They came back with a heart. And it's here on Earth. There's zero chance that they can't test this. This is what a heart is. These are the sarcomeres. These are the phospholipid membranes. This was a heart attack victim. You see that? It's all ripped apart. There's not supposed to be. They're supposed to be able to contract like this. Well, this is unfortunate here, but this is what we have here. Kind of unfortunate for this heart out there too, Bennu, but they claim there was battles in the heavens. I don't know. I'm not going to answer these kind of crazy questions of, explain it. You got to explain it. It's not have to explain anything. I am showing you what is there. You have to explain to me why it's not what I say it is. I don't have to explain to you how it got there. I don't have to speak how often a guy cut his hair. You tell me why I'm wrong. You tell me why that's not heart muscle. And why we spent billions of dollars and we can look at it and a 10-year-old can tell you it's a heart. And why we continue to deny this which we might have got free energy from. Because the white is all you want. That's all you want to put in your battery. It has no weight whatsoever. The black stays back, which is it has all the weight. The black never gets through. It's sitting around out here somewhere, because when the white comes through, it bangs into them, and then they become the Higgs fields. But this is a subatomic nuclear explosion. It literally is. And this, you see these back here? You see those waves? That's reverse EMF. That means reverse electromotive force. That's because of boom, 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 boom. That means the light is going this way and that way at the same time. Just proven that as well. Now, also proven that the black doesn't go flying back here like the white does. The black primarily goes this way. It collects here, yes, but it doesn't bounce back the way the white does. That's what's creating these fields, is the white. Bang, and bang, 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 bang. I call it push to shove, push to shove. So you push me, I shove you back. Boom, 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 boom. And it gets slower and slower and slower, and it gets tighter and tighter and tighter. Or actually wider and wider. You think of it the other way around, but see how tight it is here? And how wide it's getting out here? It's dissipating. Exactly like the magnetic field. Let's think about this carefully. You see how tight this is? It's so tight here, you can't even see it. It's just an explosion. Now it's starting to slow down. All right, I'm going to come in tight on that so you can see. You see those fields? They're really tight right there. And they get weaker and weaker and weaker as they go out. That is exactly what happens to the magnetic fields around our planet and all spinning bodies in space. You see that? It appears, and they're all dipoles. You see the black and white, black and white, black and white, black and white, all that. Some things here I have no explanation for whatsoever, and I don't have to explain it. It's here. You explain it to me. But I just showed you how they're real tight inside, and they get weaker and weaker and weaker as you go out, and as eventually they just stop. It's boop, boop. And that's what happens to light. Coming through these fields, 100% for certain it's affected. And there is no vacuum in space. It's absolute insanity to keep spending this kind of insane money to say, oh, we can measure how fast the universe is going away from us. It's pulling itself. They think light is doing this. It's pulling itself away, so it stretches. No. It's coming at us, and it's just going boom, 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 boom. And it's getting slower and slower and slower, just like this. Everything is so backwards in physics, medicine too. I mean, everything. So, Trump he's going a little on the wild side, but somebody had to do something. And now, at least, hopefully, we got a chance to start to clean up some of these things and just start looking at them a little better. We got to get something for our money, that's all. We can spend the money, but as long as you get something for the money, and we might even be able to get free energy. Now don't forget, we can separate the white, just completely separate it. We didn't do anything whatsoever other than put it through the Venturi, which is just a restriction, and the white squirted right out of there. Now, if we could push that white, here's the laser. The black stays back. The white comes through. We need to be able to harvest it right there. As simple as that. If you could put that inside of a little box like this, you carry that around with you. You put one of these in your car, you just never have to stop. Something this big might even power an airplane. That's how powerful this stuff is. Now, again, I've been showing this stuff since 2014. And I'm blocked at all the major places. I went to the University of Geneva for particle physics, and I told them we were using, they said, oh, you can't see that stuff. No, you're just crazy guy. I said, no, I'm not. I said, we're looking at particles. You're looking at chunks. At first they said, oh, no, you're going to destroy the CMOS. You can't use CMOS to do this. I said, yes, you can. If you use light. It's designed to see that. That's what CMOS does. It sees light. It doesn't see hand grenades. And that's what they're throwing at the CMOS. So anyway, they redesigned everything over there. They did. It took 3 years to redesign to be able to use CMOS. They had to harden it and do all this stuff. And this was part of the major upgrade. They put in CMOS receiver, which I told them. They said, you got to use CMOS. They were getting observer effect. Observer effects means you either are inside that area, taking energy out to say, ooh, look at that energy. Well, I'm looking at it. When I look at it, it changes, yes. Or they're putting energy in to get light to come back, and they're feeding more energy into it. They're either taking it out or putting it in. Either way, you're going to get an effect. And they thought it was just because they were looking at it. I'm not kidding you. They thought it was, they call it observer effect. They were actually making people go out of the room when they did the experiments, thinking that because they were in the room and their eyeballs were looking or something. I'm not kidding you. That's how insane they were. Now, why can't we get free electricity? I saw something that a kid, I forget where he's from, but he's working with the Chinese and everything, and he claims he did this, or did something. Made a small little device that you put in a car and never have to stop driving. And I don't know if it's true or not, because they won't talk about it. He calls it subsonic. And subsonic can, you need to drive the white away from the black. That's all you have to do, and then somehow harvest it. And just nothing more than a regular photo receiver, but a good one. You need these transition metals. You need to be able to absorb all the different frequencies of light, hopefully. If you can only absorb a couple of them, well, you see this? These are all different frequencies of light, all the way up till you get to the ultraviolet catastrophe. At that point, you're done. But you want to be able to harvest all of these in between, because those are particles of light. Those are electrons. Those are these white showers. So you need something here. I show a bunch of different colors. The colors are transition metals. This is not hard to do. And you would spray paint them on, right? Or just spray one layer, next layer, next layer, and it would be the depth of the wave. The deepest waves would be probably harvesting the shortest, you'd have to do some engineering, but you're going to have to layer. So pretty much, I would think you'll start layering down here and keep going up, and make it thicker. And the ones that, probably the red ones will go way down to the bottom. Anyway, that's an engineering thing. I started to get off on that. But if we could do this, this would and let me show you how the energy increase is right there. You're going to see something that's going to knock your socks off. See, this is the physics of electron showers. Right now they're doing proton, huge things, colliding them, hadrons, all kinds of things, flux energy, decaying hadrons, neutrino, anti-neutrino flavors. And then they get down to the electrons and the muons, which we started with. And they say if you can get to these neutrino interactions, you can get up to 100 giga electron volts. That's 100 billion, up to a few trillion electron volts. And you're only starting with, millions of electron volts. So the increase in energy is staggering, as I will show you. This is not my words. I didn't write this. This is written by CERN or Fermilab or one of the big, Lawrence Livermore, one of those. And I've tried working with every one of them, same story. All right, you see here we've been talking about muons and electron neutrinos. These are the electron showers. They come in very low energy. You see, low energy showers. They come through, they don't have much energy. However, as they shower, you get high energy showers, large showers of cones, and just exactly what I showed you. That's the white. This is the black. The muons have an earlier shower. As they hit the Venturi, they can't go through, they bounce back. And here's the muons just bouncing back here. These come through and accelerate into these huge showers, which I showed you. What happens to the energy? Why is this large energy? How much energy does it create? What could we expect to harvest out of that? We're coming in with this kind of energy, which is virtually nothing. And we get up to this kind of energy, which looks pretty substantial. Well, let's see what it looks like on a graph. Once again, not my graph. This is from, I believe, CERN, and they're talking on the order of 100,000 to 1 million base tracks. Well, all that means is the number of particles. Here they come in, and here they're coming in. Now, what happens to here? Here's the number of showers. So they're coming in, you get quite a bit just as you start into the Venturi, and then as it comes out the other end of the Venturi, that's the number of particles. So you start with here, and then you get a shower, a splash. It's like shooting a BB into a pool of water and having a splash all over. Same sort of thing. Now, what about the energy? You see that little bit of U? You see that? The little bit of U? as it comes in, these are the number of bits in the shower. It's coming in, we don't have a whole bar, and we're getting more and more and more, just like this one. And then all of a sudden we hit there, and that's energy. That U means energy. So where did we start with? Almost zip. And we're at 3,000 times. 3,000 times that. Just think of the energy that you could get out of something like this if it works, and I don't see how it can miss. I showed you what you're getting, electron showers. These are the electron showers. These are the muons backing off. I can't, how can I do this? Ram it through somebody's head? Here it is right here. You could put thousands of these little devices in here in just this little box, thousands of lasers. They're the size of a pin. And you gang them all up into a bus, drive them down. You know, when I say a bus, that's an electronic term. It's a big conductor. And you just push that white, and there's no weight whatsoever to it. And it immediately comes back to the black if you don't harvest it or use it. So you can harvest it and put it in a battery, or use it, just let it flow out to something. It'd have to be obviously engineered for, there's a bunch of different safety concerns, because you're going to have so much energy there. It's just, I can't even imagine how much energy you could get out of that. Because it's the same thing like you take a car that weighs 4,000 pounds and it's totally empty, there's no electricity in it whatsoever, you can't drive it. You fill it up with electricity, guess what? It didn't change weight, still weighs 4,000 pounds. You drive around until it's empty again, still weighs 4,000 pounds. Because all you did was put in the white. The black is the only thing that has weight. So when you look at these particles, the black part is the only part that has any weight. And this right here, which is the fixed particle. This one can get big and get small. You see it right here? Small and big. It's getting big because it's going through the air in this direction, crashing into other fields. This one's being protected by the black particles in front of it. But this one will charge up and then it'll flip, and this one will come to the front. It's called a muon wobble. And they always go up and down towards the Earth because they polarity. It's called upspin or downspin. The down particle, up particle. They have a basic, very basic understanding. I'm not kidding you. I know, he goes bragging, big shot. No, I'm not a big shot. I'm just, I see what's happening here. That's the black particle pushing the white particle in front of it. And the white particle is pushing only white particles in front of it here. This is an unusual, they call this a Whistler wave. You see that? There's no black here. The black is behind the white, pushing the white, but the white bounces the other electrons in front of it, but only the white ones. And you see these lines? These are they call them interference patterns. They're not. They're just, get away from me, I'll stay away from you. Get away, get away, get away. You see how they're just in their own little spots? I have a lot to offer. Now, Musk and President Trump, I'd like to speak. I'd like to be heard. I don't have to go. I'm not going to go anywhere. Let me put it that way. I will. I don't have to go anywhere. What do I have to go anywhere for? I can show this stuff just like that over the internet. Very easy. I do it all the time. And I think I'm doing a good job of showing the evidence to support the claims I'm making. And the claims I'm making are extraordinaire, yes. But the evidence that I am presenting is extraordinaire. There's much more to the evidence I'm showing than the things that they speculate. We've been speculating, all speculating. The speed of light can't accelerate. That's insanity. It is right there. If you can't tell us acceleration, you shouldn't even be, I don't know what you should be doing, but you sure shouldn't be doing any physics, I can tell you that. If you start out with this and then get to back what I just showed you, this is zero question that there's acceleration. And there's zero question that the universe is saturated with these particles that slow down light as they bang. The cosmic microwave background is nothing more than light that's just not going anywhere anymore. It's sort of sitting around, just sort of floating, drifting, maybe just barely moving. That's the cosmic, the whole cosmos, microwave, little bitty waves just barely moving, background, because they're everywhere. Light is everywhere all the time, and sooner or later it slows down. All right, down to the cosmic microwave background, and even lower than that, radio waves, just particles floating around in space. And the black ones, sooner or later, will collect. That's the black holes. Yes, there's no problem. I see that. That's true. Because the black ones don't mind being with each other, but the white ones want to surround them and create a crust. And it'll grow bigger and bigger, yes. And this is exactly what a black hole is. There's no difference whatsoever. You see that white crust around there? And the only reason it's sort of flattened out this way, because this is in space, it's not way out away from any real major, because this is getting sort of flat. You get more and more towards the Earth, it gets flatter and flatter and flatter. At the Earth, it's like this, so there's no way you can see how a black hole will form. But that's how a black hole forms. And because we know the blacks can separate from the white, zero question about that. We know the white is extremely attracted to the black, zero question about that. And we know that the black doesn't mind being on top of each other. They just sit around on top of each other, no question about that. It's gravity, and it sucks the white around it. This is basically the Earth, and this is basically everything that's around the Earth. You know, there's this stuff inside the Earth too. The Earth isn't completely black, but it's primarily the Earth is dark matter, and we are primarily dark matter. You wouldn't even have a finger if it was your white matter. There would be nothing there. You wouldn't be able to do that. You'd be doing this. You have to have dark matter to have any mass whatsoever. So we are primarily dark matter. And light is dark matter and energy coming through the space to interact with the Earth. And that particle and that energy makes plants grow and makes everything grow. Without light, there's just nothing. The only way there is without light is way down in the thermal vents. And the reason those are growing is because of heat. They're bubbling and boiling hot. Hot is nothing more than light going very slow. All right, do you understand? Hot, I mean, you know, infrared and heat and so forth, is nothing more than light. But it's just going slow. It's not up in the visible range of you know, ultraviolet, any of that stuff. It's way down here. Heat. It's heat. And all of this stuff is explained in dipole electron flood theory, which just happens to be right there. Dark matter goes to the center, all the different white particles, the glowy particles, go around it. The closest ones are blue because they're the tight ones. The green is a little further out, red is a little further out than that. So the red sort of is tight, but not anywhere near tight as the blue. When you rip the blue away, you're really ripping. And this shows that there's 1,839 of these particles in every proton. And these are the only two particles that exist, the white one and the dark one. I show you this, it's almost impossible to miss. And they call them gluons. I agree with that, but we separated those. Just like that, we took them right apart. And they want to be just like that so fast, instantaneously they come back together. But if you can get in between there, which we can, I know we can. I showed you we can. There's no question about that. Zero question. We can get right in there. All we got to do is get right in there before it gets there. And all that energy becomes usable. And I mean, there's a lot of energy. When you separate, you think about a tiny little battery and how long it squirts out electrons for. Just over and over and over and over and over and over. The number of electrons is so unbelievable, the number. It's just, because even in one hydrogen atom, the smallest atom that exists, the smallest nucleus, there's 1,840 of these dipole electrons. That's a lot. When you get up into upper area in the periodic table, you're up into hundreds of thousands. I don't know, I haven't figured it out, but if you took, what you have to do is take the atomic mass times 1840 or so. All right, so we need the atomic weight. All right, because atomic weight is not the atomic number. It's a little tricky. Like even helium, the atomic weight is over 4. All right, it's not just 2. All right, let's take aluminum. The atomic number is 13, but the atomic weight is almost 27. All right, there's a million different little particles in between, and there's those isotopic particles. There's a little bit to learn about chemistry, not a whole lot. It isn't as bad as it sounds. I know I make everything sound confusing, but it's really not. It's very simple. Let's just put it that way. As soon as you get down to dipole electron flow theory, you're covered. It's just these bigger and bigger balls of this. All right, the smallest one is 1840. Then the next one has 7,350 or something. It's not just 1 and then 2. Huge gaps in these numbers, and every one of them is an isotope, and every one of them is available to decay and become a daughter isotope. That's the beauty, because once you take an enzyme that works millions of times a second, it can go in and go brrr, and change these down and rearrange them up into anything it wants. Within a second, it could take that ball of particles and just turn it to a piece of bone or anything, virtually within a second. These things work millions of times a second, enzymes, to break down stuff with an enzyme. And even when it does, it's a catalyst. It doesn't even use itself up. I call it click chemistry. It comes up and it goes click, done. Otherwise, that specific reaction would take years to do if it wasn't for click chemistry, which is enzymes. All right? And an enzyme is a huge array of molecular moment signatures like that. And it has so many different spots that when it does its job, every one of them has to line up. It goes bam, and it's like lightning. Everybody that has that ability to react to that, boom. Some of them just go by; it won't bother them at all. But if it has the same dipole moments or some symbiotic relation to that, they go bam, and they just all go at once. And it's due to that like magnetic wave. It's basically. It's almost just like this. Click, so everything out there goes. I'll tell you, what a world. All right, I have just shown you neutrinos. I have found those over 10 years ago and communicated to everybody about this that is in that realm, and I was completely dismissed and blocked by virtually all of them. I was completely dismissed by 100%. Although the University of Geneva did work with me because I was a student basically going to school there. I went through Coursera. You don't even have to pay. That's fabulous. Now I don't know if they're doing it. I still get things from all the time, and it's very, very inexpensive. I think you can get an actual degree in a certain area for, I think it was like $99. That's pretty good. But anyway, that's a whole other issue. I did do this. Now, I am going to ask right now about the deep underground neutrino experiment. Now listen. What is the deep underground neutrino experiment, and how much is it costing?
The Deep Underground Neutrino Experiment, Dune, is a large-scale international scientific experiment designed to study neutrinos, which are subatomic particles that are extremely difficult to detect due to their weak interactions with matter. Neutrinos are key to understanding fundamental physics, including the origins of the universe and the matter-antimatter asymmetry. Dune is a collaboration among scientists from multiple countries, and it is led by the U.S. Department of Energy's Fermilab, Fermi National Accelerator Laboratory. The experiment will take place at two main locations. The neutrino source, located at Fermilab, near Chicago, this will produce a beam of neutrinos that will be directed to a detector. The detectors, these will be situated about 800 miles away, deep underground in the Sanford Underground Research Facility in South Dakota. The detectors are placed deep underground to shield them from cosmic rays and other background radiation that could interfere with measurements. Key goals of Dune. Study of neutrino oscillations. Neutrinos come in 3 different flavors, types, and they can change from one flavor to another as they travel. Dune aims to study this process of neutrino oscillations in great detail, which could help explain why the universe is made mostly of matter rather than antimatter. Search for CP violation in neutrinos. This would help understand why there is more matter than antimatter in the universe. Study of supernova neutrinos. Dune will be able to detect neutrinos from distant supernovae, helping scientists study these cataclysmic events in unprecedented detail. Search for physics beyond the standard model. Dune will help test whether neutrinos have additional properties that the standard model of particle physics cannot explain. Cost of Dune. The total cost of the deep underground neutrino experiment is estimated to be around $1.5 billion USD. This funding includes the construction of both the neutrino beamline at Fermilab and the large detectors in South Dakota, as well as the infrastructure necessary to support the scientific work. The project is expected to span several years, with construction and data collection taking place over the next decade or so. In addition to the U.S. Department of Energy, the experiment has contributions from international partners, including countries like Italy, the UK, and others, who are collaborating on various aspects of the project. Overall, Dune is one of the most ambitious neutrino experiments ever undertaken, aiming to answer some of the deepest questions in physics.
Okay, I think I showed you pretty good evidence to support dipole electron flood theory. Now let's see what would change if dipole electron flood theory were correct. What would change in physics and everything else if dipole electron flood theory were proven to be correct?
If the dipole electron flood theory were proven to be correct, it could potentially lead to a fundamental shift in our understanding of physics and the nature of matter and energy. However, it's important to clarify that the dipole electron flood theory, as a specific term, isn't a widely recognized or established theory in mainstream physics as of now. But if we were to hypothesize a theory involving dipole electrons, electrons with distinct positive and negative poles, or a new model of electron behavior, several consequences could emerge if this theory were proven correct. Let's break this down. 1. Revision of quantum mechanics and particle physics. Electron properties. The standard model of particle physics treats the electron as a point particle with a negative charge, which doesn't have a dipole moment, at least not in the traditional sense. If the electron were found to have a dipole moment or behave in a way that's inconsistent with current models, this would require a complete reevaluation of quantum field theory, which is the foundation for understanding particle interactions. New physics beyond the standard model, proving the existence of dipole electrons, could provide evidence for a new framework of physics beyond the standard model. It might open the door for new particles, fields, and forces that we haven't yet observed. This could also have implications for dark matter or dark energy, which remain mysterious areas in physics. 2. Impact on electromagnetic theory. Electromagnetic interactions. Electrons are central to our understanding of electromagnetism, as they are responsible for electric charge and currents. If electrons are dipoles, it could lead to modifications in how we understand electromagnetic interactions, possibly affecting everything from classical electromagnetism to the quantum electrodynamics (QED) that currently governs particle interactions. Changes in electric and magnetic fields. If electrons had an intrinsic dipole moment, the way they interact with electric and magnetic fields would change, potentially affecting the behavior of atomic and molecular systems. This could influence how materials respond to magnetic fields or how we understand atomic structure. 3. Potential for new technologies. Advances in technology. If electrons behave differently than we currently understand, it might lead to breakthroughs in technologies that rely on electron behavior. For instance, semiconductors, computers, and quantum technologies could all experience significant changes, potentially leading to more efficient or novel devices. Energy generation. A new understanding of electron behavior could revolutionize energy generation and storage methods. For instance, if the dipole nature of electrons could be harnessed in a new way, it might unlock new forms of energy harvesting, storage, or even propulsion technologies. 4. Cosmological and astrophysical implications. Understanding of the universe. If the dipole electron flood theory leads to a new model of electron interactions, it could change our understanding of fundamental forces in the universe. This might influence models of how galaxies form, how stars evolve, and the behavior of black holes, for example. New insights into the early universe. New electron properties might offer insights into the conditions of the early universe after the Big Bang, potentially leading to new theories about cosmology, the formation of the universe, and the fundamental forces. 5. Philosophical and conceptual shifts. Redefinition of matter and energy. If electrons are found to possess properties we didn't expect, this could challenge fundamental concepts of matter and energy. For example, it might change how we view the particle-wave duality or force us to reconsider concepts like the conservation of energy. Impact on the Standard Model. A proven dipole electron flood theory would call for an extensive modification of the Standard Model of particle physics. It could lead to a paradigm shift in how we conceptualize particles and forces, which would also affect how we understand the universe at a fundamental level. In conclusion, the exact implications of a proven dipole electron flood theory depend on the specifics of the theory itself, but in general, such a discovery would likely trigger a major overhaul of current scientific models, particularly in fields like quantum mechanics, electromagnetism,
and cosmology. It would expand our understanding of the fundamental particles and forces that govern the universe and could lead to a new technologies or even a new era in scientific research. It has to. For now, though, as the dipole electron flood theory is not an established part of mainstream physics, its potential impact remains hypothetical. Still, any theory that challenges existing models could profoundly change the landscape of scientific knowledge and technological progress. Now, why am I blocked from our national laboratories that are supposed to be looking for these particles that I think I have just shown we have discovered? If all of this is the result of dipole electron flood theory being correct, we have really missed the boat. For many years now. This is not just a year or 2 years or 3 years or 5 years. This goes back well over 10 years. This was done and known over 10 years ago and blocked by the ones that we pay billions of dollars a year to get hopefully something valid and to block this information for this amount of time. It's very distressing. So I'm hoping that Musk and President Trump, Vice President Vance, somebody will step up and say, look, let's just take a look at it. That's all. Just take a look at it. Don't have to go crazy. If it makes sense, it makes sense. If it doesn't, well, it's just another thing that doesn't make sense. I'm not the first one that came along with something that might not make sense. They check into everything. They look at the craziest things because there's a bunch of funding in it. My stuff is already done. There's no more funding to speak of. It's very, very small. In a week or two, it'll be off the table. Either it works or it doesn't work, and you go on from there. If you go on from there and it works, we are golden. If it doesn't work, we're just back in the same soup again. All right, this is time to take a look at something that's quite obviously promising. Okay, I think that's a pretty good case I made. And when they talk about having flavors of these neutrinos, well, they do. They get stronger and stronger and stronger as they get more and more close to being impacted. They're building up against their own fields. Let me show you the actual evidence about them. Okay, they're talking about these neutrinos getting flavors. Flavor just means more and more energy. And here's what it is. These are the photons here, and here is the Venturi. You don't see photons until they gain enough energy. And why are they gaining energy? Because they're getting bounced into their own waves. They're just bouncing back. So this one's getting a little bit of energy. Up here, they don't get any bounce back at all to speak of because they're not directly in line. So the field is coming back this way. And so these start to glow a little bit, and they're sideways, like Oreo cookies. And then they go this way. And we're starting to see the photon, though, right exactly in line with the Venturi, show up here as a true photon. But it's kind of flat. You see how that's flatter? If you look at this carefully, you can see some really subtle differences, and you can see a bunch of dust. All right, now, what do you see there? That's a flat photon. Now, if we come over here, it gets a little puffier and a little more glowy. And then when it hits the Venturi, the case is closed. And now you have that reverse EMF coming back. That's the only reason these are showing up. So you never see those. Back here, there's just nothing there. Not even nothing whatsoever. But now they're in this field of reverse EMF. Now, another thing I told you before is they're always straight up and down to the Earth because they're polar. And they're going to be straight up and down. Even if they were going this way, the particle wouldn't be spinning this way. It would still be spinning this way, but moving up. So it would be going like this, going up. And I can show you that in the green. Same particle, black and red in that case, and this is black and green. And these are the same different flavors of the neutrinos. And they're gaining energy as they're starting to go. Now, you see how this is straight up and down this way? Even though it's going that direction, it's straight up and down because it's polarized to the Earth. Now, here you can see the white is in the front and it's getting charged up, ready to flip. That's why it's all fuzzy looking. And it'll flip, and that one there will come to the front. All right, here they're pretty well even. Here, this one's charged up more than that one. Now let me show you how that happened in the red. You don't see it happening in the red because red is very slow. But this one here, you see the lower part is white is in the back. So this is, excuse me, that's called an upspin. Now the lower part is the white is in the front, that's a downspin. That's it. And here's where it really bangs here, and this is all coming back. And that's the only reason you see all those other fields. You would have never seen them. You see these fields here? You would have never even seen these. But now they're just glowing like on steroids because of the push back. That's not the glow. This one here is glowing because it's coming forward. These are glowing like crazy because they're right in the middle of the explosion. And that literally is a subatomic nuclear explosion. Fission and fusion. Raw white electricity. That's electricity. Same thing as static, same thing as lightning, and the same thing as electricity. When you only have one electron dipole. Let me just back this up so you understand this fully. Let's get back to dipole electron flood theory. All right. That right there has no mass whatsoever that I can find. That's the energy. And you have to pull those two apart. And boy, you just can't hardly do it. It's almost impossible. The only way they can do it is with a real good generator. And when you turn a generator on, you hear it go, what is it doing? It's trying to pull these apart with a magnetic field. And it does. And you can generate electricity doing that, but you have to pull a hell of a lot of energy in. We did nothing, zero. We funneled it together and it came out the other side with energy. Through the roof, if that's right. I just showed you 3,000 times. 3,000 times they show on this chart. If that's right, that's right. Started off way down here. That's energy. U means energy, maximum energy. Whew. If that happened, wow. And it weighs nothing. It has no weight. It's not like it to carry a huge battery around. It has no weight. All right, I know I went real long on this, but one more shot here. This is the Higgs fields. Now, they think the Higgs fields is when they separate. No, the Higgs fields is when they come back together. This is white is coming all by itself here, and it's hooking up with the black particles. You see right here? You see white, black, white, black, white, black, and then it turns into these disks with an internal magnetic field. That's an internal magnetic field, and that virtually is identical to the light that was coming in from the other side and was split. It went from light back to light. All right, remember this now. This is where the white comes through and it rejoins with the black. Well, when it split apart, it was looking basically the same thing. Here it was coming in and it split apart here, and here's where it's coming back. It's got the same fields as they recombine. Very strange. But it's like you separated it here and it comes back over there. And it wants to come back so bad that it will drive your car like crazy. And electricity is just staggeringly powerful. And it can be separated from the black. I'm going to show you one more thing about the black being separated from the white, an atomic bomb blast, and then I'm going to close this up because it's gone forever. But I need somebody in our government. This is not a $50 deal. This is hundreds of billions of dollars. Hundreds of billions. And maybe we can save the planet with free energy. And that has been refused even to be examined.